Tonight, we're going to explore one of the most beautiful and deceptive worlds in our solar system. From nearly 1 billion miles away, Saturn appears almost peaceful. Its pale clouds look smooth. Its rings seem perfectly arranged. It hangs in space like something permanent, untouched by the violence surrounding it. But almost everything about that image is misleading. Saturn has no solid surface to stand on. Descend through its clouds, and the atmosphere grows darker, hotter, and more crushing until hydrogen itself is forced into an exotic metallic state. Winds race around the planet at more than 1,000 kilometers per hour, while storms large enough to swallow Earth churn beneath a seemingly calm exterior. Even its rings are temporary. The ice particles that form Saturn's crown are slowly falling into the planet as a continuous rain. In less than 100 million years, the rings that define Saturn may be gone completely. And beyond them, its frozen moons may be hiding something even more extraordinary. Vast oceans sealed beneath layers of ice, where the conditions for life could exist in complete darkness. Saturn is not a quiet ornament at the edge of the solar system. It is an enormous, changing world, born from chaos, consuming its own rings, and surrounded by moons that may be keeping secrets from us. By the end of tonight, you're going to understand how Saturn emerged from the violent birth of the solar system, why its famous rings are actively disappearing during the narrow period in which we happen to exist, and what may be waiting beneath the ice of its most mysterious moons. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Saturn's calm appearance gives no hint of the violence that created it. To understand how this enormous world came to exist, we have to travel back beyond its rings, beyond its moons, and beyond the planets themselves, to the beginning of our solar system. Around 4.5 billion years ago, there was no Saturn, there was no Earth, there was not yet a sun. There was only a vast cloud of gas and dust, cold and dark, slowly drifting through one arm of the Milky Way. Then something disturbed it. A nearby star may have exploded, sending a shockwave through the cloud. Another gravitational disturbance may have pushed part of it beyond the point of stability. The exact trigger remains uncertain, but the result was irreversible. Gravity began pulling the cloud inward. As it collapsed, it spun faster, flattening and heating until pressure at its center became intense enough for a new star to ignite. That was our sun. The remaining material did not disappear. It spread into a wide, rotating disk surrounding the newborn star. Within that disk were the remnants of older stars, hydrogen and helium, but also iron, silicon, carbon, oxygen, and water ice. Everything that would eventually become a planet, moon, asteroid, or comet was already there, mixed together and waiting. Inside that disk, material began to clump, not quickly, not all at once. Grain by grain, pebble by pebble, rock by rock. Small bodies called planetesimals grew by collision and gravity. The process was patient, the process was violent, and the process produced very different results depending on where in the disk it was happening. Here's where the story divides. Close to the sun, temperatures were high. Only metals and silicates could survive the heat. The building blocks of the inner solar system were dense and rocky. Mercury formed, Venus formed, Earth formed, Mars formed, all of them small, all of them dense, all of them baked by solar radiation into compact rocky worlds. But further out, something different was happening. Roughly where Jupiter's orbit sits today, the temperature crossed a threshold. Scientists call it the frost line. Beyond it, it was cold enough for water ice to exist as a solid. And that mattered enormously, because ice was not rare. Ice was everywhere. Far more abundant than metal or silicate, ice multiplied the supply of solid building material by orders of magnitude. The cores forming beyond the frost line had more to work with. They grew larger. They grew faster. And eventually some of them grew large enough to cross a threshold that changed everything. When a core reached roughly 10 Earth masses, something different happened. Not gradual accretion anymore. Not grain by grain. The core's gravity became strong enough to reach out and capture something it couldn't capture before. Gas. Hydrogen and helium, the most abundant materials in the disk, began falling onto the core not in trickles, but in torrents. The core acted like a seed. The gas acted like a flood. And once the flood began, it didn't stop. The planet's mass doubled, tripled, kept climbing. This is how gas giants are born. Not gently. In a runaway. Jupiter crossed that threshold first. Jupiter formed closer to the frost line, where the material was densest. It assembled its core faster than anything else in the outer solar system. It triggered the runaway earlier. By the time Saturn was still building, Jupiter was already enormous, its gravity reshaping the gravitational landscape of the outer disk, funneling material, disturbing orbits, claiming the largest share of everything available. Jupiter today holds roughly 318 Earth masses. Saturn holds roughly 95. That gap is not a coincidence, and it is not a mystery. Jupiter got to the buffet first and took the largest share. Saturn arrived second and worked with what remained. But here's where it gets strange. Saturn's later arrival forced a different kind of growth. It kept accumulating its core longer while pulling in a proportionally thicker envelope of hydrogen and helium relative to its total mass. The result was a planet built differently from Jupiter at a structural level, not just smaller, differently proportioned. More gas relative to rock, more puffed, more distended. A balloon of gas wrapped around a core that may not even be solid anymore. And that difference has one consequence that stops people cold. Saturn is the second largest planet in the solar system. It is 95 times the mass of Earth. It is enormous by any reasonable measure, and yet it is less dense than water. Not slightly less dense, dramatically less dense. If you could find an ocean large enough, Saturn would float. Not sink, float. That single fact tells you everything about how this planet is built. Mostly hydrogen, mostly helium, puffed up and distended, shaped by the accident of arriving second, in a race that was decided 4.5 billion years ago. Deep inside that balloon, there is a core. Scientists believe it exists, but whether it is solid at all is something they still cannot agree on. That question is not settled. It will come back. For now, the important thing is this. Saturn is what it is because of where it formed and when. The entire structure of this planet, the low density, the strange interior, the vast gas envelope, traces directly to one moment. Jupiter won the runaway first. Saturn built what it could from what was left. And what was left produced one of the most unusual objects in the solar system. That was only the beginning of the strangeness. The planet was built. Now it had to survive the neighborhood. And the neighborhood, in those early hundreds of millions of years, was not the orderly arrangement of worlds we see today. The solar system we know, with its planets moving in calm, predictable paths, its distances measured and catalogued, its structure apparently fixed, is a picture taken long after the battle ended. What happened before that picture was taken is a different story entirely. Here is what scientists believed for a long time. The planets formed roughly where we find them, settled into stable orbits, and stayed. The solar system was essentially built in place. Orderly, gradual, peaceful. They were wrong. Not slightly wrong. Catastrophically wrong. The best model we now have for the early solar system's violent history is called the Nice model, named after the city in France where it was developed. In 2005, a team of 4 researchers, Alessandro Morbidelli, Rodney Gomez, Cleomenes Tsiganis, and Harold Levison, published a series of landmark papers in the journal Nature. What those papers proposed overturned the old picture completely. The giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form in the orbits they occupy today. They formed packed together much closer to the Sun, in a compact configuration stretching roughly from 5.5 to 17 astronomical units. Beyond them, undisturbed, lay a vast disk of icy bodies, planetesimals left over from the solar system's formation, billions of them, slowly orbiting in the cold and dark. For hundreds of millions of years, that arrangement held. The planets moved in their compact paths. The disk waited. Then the balance broke. Jupiter and Saturn drifted, slowly, through tiny gravitational nudges accumulating over time, into what scientists call a 2.1 mean motion resonance. A resonance is a gravitational lockstep between 2 orbiting bodies. The 2-1 means that for every 2 orbits Jupiter completed, Saturn completed exactly 1. Their gravitational pulls began to align and reinforce each other on a regular rhythm. It was like 2 musicians accidentally synchronizing their timing and, in doing so, shaking the stage. The effects did not stay between Jupiter and Saturn. They rippled outward. Uranus and Neptune were kicked onto wider, more eccentric orbits. paths that were no longer smooth circles, but stretched ovals that carried them swinging further from the sun and back. One of them, possibly Neptune, was driven outward directly into the great icy disk. And here, the analogy the science itself reaches for is the right one. It was like a bowling ball thrown through pins. Neptune, a world 4 times the diameter of Earth, plowed through billions of icy bodies at gravitational speeds. The disk did not survive intact. It shattered. Some of those icy bodies were flung outward. They gathered at the far edges of the solar system and became what we now call the Kuiper Belt, the broad ring of frozen objects beyond Neptune, and the Oort cloud, the vast spherical shell of comets at the solar system's outermost limit. Both of those structures, which today feel like permanent fixtures of our neighborhood, were assembled from the wreckage of this single event. Others were hurled inward. The inner solar system, where the rocky planets had already formed and quieted, was hit by a barrage. Scientists call it the Late Heavy Bombardment. The craters that scar the face of the moon, some of them hundreds of kilometers across, visible on a clear night with nothing more than a naked eye. Many of those craters are thought to trace back to this period. The ancient impact basins on Mars, the scarred surface of Mercury. The signatures of bombardment are written across the inner solar system in rock and dust, and a gravitational tantrum triggered by the dance of Jupiter and Saturn may have written all of them. But here is where it gets strange. The cascade may have done more than scatter icy bodies and pummel rocky planets. Computer simulations run by David Nesvorny at the Southwest Research Institute found something unexpected. When researchers modeled the instability using the 4 giant planets we know today, the simulations repeatedly produced orbital configurations that did not match our actual solar system. The planets ended up in the wrong places, with the wrong spacings. When the team added a 5th giant planet, an additional ice giant roughly the size of Neptune, the simulations suddenly worked. The numbers matched. The final orbits aligned with what we observe. The implication is unsettling. The early solar system may have contained 5 giant planets, not 4, and one of them may no longer be here. During the instability, that 5th world, a Neptune-sized ice giant, may have been thrown into a close encounter with Jupiter. Jupiter, far more massive, won that encounter decisively. The smaller world was ejected, not pushed to the edges of the solar system, not captured somewhere distant, ejected entirely, thrown out into interstellar space. Think about that for a moment. There may be a planet, a world the size of Neptune, wandering the galaxy right now in complete darkness. No star to orbit, no light to receive, alone in the void between the stars because Jupiter and Saturn rearranged the neighborhood 4 billion years ago. We have not seen it. We do not know where it is. We may never know. It is a ghost written into the mathematics of what survived. The simulations support this. The actual existence of that world remains uncertain, not confirmed, not ruled out, held in the careful space between what the models suggest and what we can directly observe. Saturn at least survived, but survival came with consequences. The orbit Saturn occupies today, roughly 9.5 astronomical units from the Sun, is not the orbit it was born into. The same gravitational interactions that scattered the icy disk and ejected that possible 5th world pushed Saturn outward. Its current address in the solar system was assigned by the chaos, not by its original formation position. Its axial tilt, roughly 27 degrees, the angle at which it leans relative to its orbit, was likely shaped by encounters during this same violent period, and the collection of moons that would later gather around Saturn, some formed from debris, some captured, some broken apart and reformed, bear the fingerprints of that reshuffling. The Saturn we see today through a telescope, golden and serene and impossibly beautiful, surrounded by its rings, lit from the side by the sun, is a survivor of a war. Not a war fought with weapons, a war fought with gravity, a war in which entire worlds were flung outward into the dark, others were driven into the sun, and at least one, perhaps, was expelled from the solar system forever. Every orbit in our neighborhood was changed by this event. Every moon, every ring, every crater on every rocky world. The architecture we call home was assembled from the aftermath. Saturn did not inherit its place peacefully. It claimed that place through something the science describes as gravitational natural selection. The planets that could not adapt to the chaos were broken apart, swallowed by the larger worlds, or thrown into the dark. Saturn endured. It emerged from the instability in the orbit it still holds today, battered, tilted, reshaped by the violence it survived. That survival would shape everything that followed. And what followed for Saturn is written in the rings. What the war left on the outside of Saturn was written in its orbit, its tilt, its moons. But the war left something stranger within. Something that would stay hidden for decades, buried beneath those calm banded clouds, invisible to every telescope and every flyby that had ever passed this world. It took a different kind of listening to find it. In 2004, the Cassini spacecraft arrived at Saturn. It had travelled 7 years to get there, crossing the cold outer reaches of the solar system, and when it finally settled into orbit, it began doing something no spacecraft had done before. It began peeling back the layers. Here is what scientists believed at the time. A gas giant like Saturn had a solid core at its centre. Compact, discrete, made of rock and ice. The rest of the planet, the vast envelope of hydrogen and helium, floated around that core like atmosphere around a stone. The image that captures it cleanly is a pit inside a peach. A firm, distinct centre surrounded by softer material. One thing ending clearly where the other begins. That was the textbook picture. Planetary scientists had built their models around it for decades. Cassini did not confirm it. It overturned it. The first clue came not from inside the planet at all. It came from the rings. Christopher Mankiewicz and Jim Fuller, researchers at the California Institute of Technology, were studying patterns in Saturn's innermost rings when they noticed something that should not have been there. The rings were not perfectly smooth. They contained waves, faint ripples, structures that seemed to respond to something happening deep inside the planet. Mankiewicz and Fuller realized what they were seeing. Saturn was quivering. The planet was oscillating, vibrating at its own internal frequencies, the way a bell vibrates after it has been struck. And those vibrations were traveling outward through the planet and imprinting themselves on the innermost rings. The rings were acting as a seismograph. Think about what that means. We had spent decades designing probes and instruments to study planetary interiors. We had assumed that to understand what was inside a world, you would have to send something inside it. But Mankiewicz and Fuller found a different way. They read the surface of the rings the way a geologist reads a seismograph needle after an earthquake. And from those patterns, they reconstructed what was happening in the core. What they found did not match the textbooks. Not a pit inside a peach, not a solid ball of rock and ice at the center. What they found was something far stranger. A gradient. Heavy elements, rock, ice, dense compounds, did not stop at a sharp boundary and give way to gas. They dissolved upward, gradually, smearing into the hydrogen and helium envelope in a slow, diffuse transition that extended outward to roughly 60% of the planet's radius. Not the inner 10% or 20%, 60%. More than half the width of the entire planet. A blurred and sloshing mixture of material with no clean edge anywhere inside it. Scientists gave this structure a name. A fuzzy core. Not solid, not liquid, not gas. Something in between. Something that defies the categories the textbooks used. The total mass of this core region came to roughly 55 Earth masses of material. Of that, about 17 Earth masses were rock and ice in any recognizable form. The rest was hydrogen and helium, mixed and layered and blended through a zone so large that the old Peach Pit model looks almost embarrassingly tidy by comparison. And it was still moving. Not static, not settled, sloshing. But the implications did not stop with Saturn. This discovery did not only change our understanding of Saturn, it changed our understanding of every giant planet. If Saturn's core is a smeared gradient rather than a clean solid ball, the question becomes immediate. What about Jupiter? Jupiter, which formed before Saturn, which claimed the largest share of the available material in the early solar system, which has been the dominant planet in our neighborhood for 4.5 billion years. Does Jupiter have a fuzzy core too? Researchers who turned similar techniques toward Jupiter's data found evidence suggesting it does. The same smearing, the same diffuse transition, the same structure that the textbooks had not predicted and the models had not prepared for. Think about the implication. We did not just misunderstand Saturn. We may have misunderstood how all giant planets form. The clean textbook picture assumed that a rocky core grew first, gas piled on top, and the two stayed separate. A neat layered world. One thing inside another. But a fuzzy core tells a different story. It suggests the process is messier than that. More turbulent, more gradual, with heavy elements mixing upward into the hydrogen envelope throughout the formation period, never fully separating, never settling into clean strata. Not a structured construction, layer by careful layer. A slow dissolving. A blending that never resolved. And if Saturn formed that way, and Jupiter formed that way, perhaps every gas giant in every solar system across the galaxy formed that way. Perhaps the smear is the rule, and the clean textbook core was always the fiction. Saturn was born in violence. It endured the chaos of the instability, claimed its current orbit through gravitational luck and mass, and carried forward into the present a structure so strange that even now, decades after Mankiewicz and Fuller's work, scientists are still arguing about what it means. Still arguing about the exact shape of the gradient. Still arguing about whether the sloshing is uniform or structured in shells. Still arguing about whether the mixing is ongoing or frozen into place. The fuzzy core is not a solved problem. It is an open one. And the tool that revealed it, the rings reading the planet's heartbeat from the outside, had more to say. The rings themselves were not simply a passive seismograph. They had their own story, their own age, their own approaching end. That story would turn out to be as strange as anything Cassini found beneath the clouds. We have just used the rings to see inside a planet. It is worth asking what they are. The story starts in 1610. Galileo Galilei turned his telescope towards Saturn and saw something that made no sense. The planet appeared to have ears, two blurry lumps, one on each side, flanking the disk like handles on a pot. His optics were too crude to resolve what he was actually seeing. He drew them as rounded protrusions and wrote letters speculating that Saturn might be accompanied by two large moons pressed unusually close to its sides. Then, 2 years later, he looked again. The lumps had vanished. Saturn appeared perfectly round, serene, and featureless. Baffled, he reportedly asked whether Saturn had devoured its own children. It was a reference to the Greek myth of Kronos, the titan who swallowed his sons to prevent them from overthrowing him. The question was equal parts frustration and genuine bewilderment. Galileo never solved the mystery. He died without an answer. 45 years passed. In 1655, the Dutch astronomer Christian Huygens pointed a far better telescope at the same planet. What Galileo had seen as ears, Huygens resolved as something no one had previously described in all of astronomy. A flat ring, a thin, continuous disk, encircling Saturn completely, but not touching it, tilted at an angle to the line of sight, which was why it sometimes appeared broad and open, and sometimes edge-on and nearly invisible. Galileo's ears were the ring's two sides, catching the light. The disappearance was the ring turning edge-on. Huygens had it right, but something was wrong. Huygens described one ring, a solid, continuous band around the planet. That is what it looked like. That is what every illustration since has suggested. And for 2 centuries, no one seriously questioned it. Then James Clerk Maxwell did. In 1859, the Scottish physicist Maxwell approached the problem mathematically. He asked a simple question. Could a solid ring actually orbit Saturn? He worked through the mechanics carefully. A rigid solid ring, he showed, would be gravitationally unstable. The tidal forces from Saturn would tear it apart. The forces from Saturn's moons would cause it to wobble and eventually collide with the planet itself. A solid ring, in Maxwell's mathematics, was impossible. Not a solid band, not a continuous rigid sheet. The rings had to be made of countless individual particles, each one orbiting Saturn independently, like a miniature moon, following its own path around the planet and simply appearing from a distance to form a continuous structure. Maxwell was right. It would take another century and the tools of modern spectroscopy to confirm it directly. But the conclusion was correct. What looks from Earth like a painted band is actually a swarm. Trillions upon trillions of separate pieces of water ice, each drifting in its own orbit, each governed independently by Saturn's gravity. Think about what that means. The most visually stunning structure in the solar system, the one that looks in photographs like a smooth, polished disk cast from solid material, is not solid at all. It is closer to a crowd than a wall. A vast thin crowd of ice particles ranging in size from grains smaller than sand all the way up to chunks as large as houses. Some are clear as glass, some are dusted with organic compounds and silicate impurities, giving them a faint brownish tint. All of them are moving. Together, they span roughly 175,000 miles from the inner edge to the outer. But scale that down. Imagine you shrink the entire ring system to the width of a football field. At that scale, the rings would be no thicker than a razor blade, often no more than 30 feet from top to bottom, at their thinnest, for a structure wider than the distance from Earth to the Moon. That is not a ring. That is a film. The rings are not uniform, they are divided into named sections, each with its own density and character. Moving outward from the planet, the innermost visible ring is the D ring, so faint it barely registers, grazing the edge of Saturn's upper cloud deck. Then comes the C ring, sometimes called the crepe ring, translucent and dim. Then the B ring, the broadest and most massive, reflecting more light than any other part of the system. Then the A ring, bright and dense, separated from the B ring by a gap roughly 3,000 miles wide. That gap has a name. Giovanni Domenico Cassini discovered it in 1675, and it carries his name to this day, the Cassini division. It looks empty. It is not entirely empty, but it is dramatically depleted compared to the rings on either side. And far beyond the main rings, diffuse and enormous, lies the E ring. Not ice chunks, tiny particles, a vast faint halo fed continuously by geysers erupting from the surface of Enceladus, one of Saturn's moons. The E-ring exists because Enceladus is pumping material into space right now. All of this raises an obvious question. Why are the rings here at all? Why do they exist in this specific zone around Saturn and not somewhere else? The answer lies with a French astronomer named Edouard Roche. In 1848, Roche calculated something that would later become one of the most important concepts in planetary science. He identified a boundary, a specific distance from a planet within which tidal forces become overwhelming. Tidal forces arise from the difference in gravitational pull between the near side and the far side of any orbiting body. The near side of a moon is always pulled toward the planet slightly more strongly than the far side. On large scales, that difference is small, but close enough to the planet, it becomes enormous. Roche worked out the distance at which those tidal forces exceed the internal gravity holding a body together. Cross inside that line, and a body cannot hold itself as a unit. It gets torn apart. The near side gets pulled faster than the far side. The body stretches and fragments. The Roche limit, as it came to be called, is an invisible line of destruction drawn around every planet in the solar system. For Saturn, with its relatively low density, the classical Roche limit for an icy body sits at roughly 2.5 Saturn radii from the planet's center. Now, look at where Saturn's rings are. They lie almost entirely inside that boundary. That is not a coincidence. Inside the Roche limit, no moon can hold itself together through gravity alone. A moon that drifts too close or forms too close cannot accrete. It gets shredded. The pieces spread out in orbit. They collide gently, losing energy, settling into a thin plane. They become a disk. They become a ring. The Roche limit is not a passive feature of Saturn's geometry. It is the mechanism, the process that shredded the material, the process that keeps that material from reaccumulating into a moon, and, as it turns out, the process that is still active today, slowly grinding the rings down and pulling their particles inward toward the planet. Every planet in the solar system has a Roche limit. Earth has one. Jupiter has one. Even our own moon would be torn apart if it somehow spiraled close enough to Earth. The concept is universal. But at Saturn, the Roche limit is not a textbook abstraction. It is something happening right now, around a planet you can see on a clear night, through a cheap telescope. The most beautiful structure in the solar system exists because of a mathematical boundary calculated by a French astronomer in the middle of the 19th century. And that same boundary is, at this moment, destroying what it made. The rings had an origin, and that origin, it turned out, was far stranger and far more recent than anyone had expected. That last phrase deserves a longer look. The rings are being destroyed, slowly, steadily, pulled inward by the same boundary that built them. And once you start measuring how fast, a much stranger question opens underneath it. Not about the future of the rings, about their past. For most of the 20th century, scientists assumed the rings were ancient, not hundreds of millions of years old, not a billion. Ancient in the deepest sense, primordial, relics of the solar system's earliest moments, material that had orbited Saturn since the planet itself formed, 4.5 billion years ago. The assumption was reasonable. Saturn was old. Its moons were old. The rings sat inside the Roche limit, where material could never coalesce into a larger body, so they had simply stayed there, frozen in orbit, while the rest of the solar system grew up around them. That was the picture. Stable, timeless, essentially permanent. Then Cassini measured them. Cassini orbited Saturn from 2004 to 2017. For most of that mission, the spacecraft stayed safely outside the rings, observing from a distance. But in its final months, in the maneuver scientists called the grand finale, Cassini changed its orbit dramatically, threading the narrow gap between Saturn and the innermost ring 22 times before its planned plunge into the planet's atmosphere. Those 22 orbits gave scientists something they had never had before, a direct measurement of the ring system from the inside. And what they found did not match the ancient picture at all. 2 measurements, 2 surprises. The first was the mass. Cassini detected the gravitational signature of the rings during those close passes, and the numbers came in strikingly low. The rings have a mass of roughly 40% the mass of Mimas, Saturn's smallest major moon. That is not much. Think of it this way. Mimas is a world roughly 250 miles across, and the rings contain less than half its total mass, spread across a disk hundreds of thousands of miles wide. A lower mass means less inertia, less ability to resist change, less resilience against the forces already eroding them. The rings, despite their visual grandeur, are surprisingly fragile. The second measurement was stranger. Sascha Kempf, a physicist at the University of Colorado Boulder, led a team analyzing data from Cassini's cosmic dust analyzer. Their question was simple. How much interplanetary grime settles onto the rings each year? Space is not empty. Dust drifts through the solar system constantly. The fine debris of comets, asteroids, ancient collisions. Some of it lands on the rings. Kempf's team calculated the rate, less than a gram per square foot annually. That sounds insignificant, but over billions of years, even a fine, slow sprinkle accumulates. If the rings had truly been sitting there for 4.5 billion years, they should be dark, stained by eons of accumulated contamination. Ancient things get dirty, but the rings are not dark. They are strikingly, almost improbably bright, pure white water ice, clean as fresh snow. Think of a white carpet laid down in a house. Dust settles on it immediately, dirt tracks in, stains appear. A carpet that has been down for decades looks like it has been down for decades. Saturn's rings should look like that. Old, grimy, dark with time. Instead, they look like the carpet was unrolled yesterday. The whiteness is not a surface phenomenon, it is evidence that the rings are new. Kempf's study, published in Science Advances in 2023, put a number to it. The rings are no more than 400 million years old. Other analyses using Cassini data pushed the estimate even younger, perhaps as low as 10 to 100 million years. The precise age is unsettled, and scientists are still working through the data. But the direction is clear. The rings did not form with Saturn. They arrived late. In geological terms, Saturn acquired its rings recently. Possibly so recently that dinosaurs were already walking the Earth when the rings appeared. Not ancient, not primordial, young. But that answer immediately raises a harder question. If the rings are not leftover material from Saturn's birth, what created them? Material does not simply appear inside the Roche limit. Something had to put it there. And something that size, concentrated that close to Saturn, forming that recently, means something was destroyed. The leading explanation points to a murder. Jacob Kegaris, a scientist at NASA's Ames Research Center, ran supercomputer simulations of the problem. His team modeled nearly 200 different collision scenarios, varying the size, speed, and impact angle of precursor moons, the icy worlds that may have orbited Saturn long before the rings existed. In scenario after scenario, the right kind of collision between 2 icy moons produced exactly the right result. A spray of ice and debris inside Saturn's Roche limit, where tidal forces would then spread it into a thin disk matching the one we observe today. The trigger for the collision may have been orbital resonance with the Sun. Saturn's moons migrate outward slowly over time, pushed by tidal interactions. As they move, some pass through zones where the Sun's gravity creates a cumulative destabilizing effect, slowly stretching and tilting their orbits until trajectories cross and impact becomes inevitable. Saturn's moon Rhea currently orbits just beyond one of these resonance zones. Had Rhea been migrating for long enough, it would have crossed that zone relatively recently in astronomical terms. The implication is that the collision was not random. It was, in a sense, arranged. Saturn's rings are not the peaceful remnant of formation. They are the remains of one or two moons shattered by collision, their ice and rocks scattered into orbit, ground by tidal forces into the luminous disk we call the rings. The rings are a crime scene, and the evidence is still falling. But the reality was different. The same forces destroying that evidence are still at work. James O'Donoghue, a planetary scientist at NASA's Goddard Space Flight Center, led research published in Icarus confirming that Saturn is losing its rings at what he described as the worst-case scenario rate. Ice particles in the rings become electrically charged, either by ultraviolet radiation from the sun or by micrometeoroid impacts. Once charged, they no longer behave purely as orbiting objects. They respond to Saturn's magnetic field, sliding along invisible magnetic field lines and falling into the planet's atmosphere at mid-latitudes. Scientists call this ring rain. The rate is not slow. Ring rain alone drains enough water to fill an Olympic-sized swimming pool every 30 minutes. Add the equatorial infall that Cassini measured during the grand finale, material spiraling directly into Saturn's equator under the combined pull of gravity and atmospheric drag, and the total loss rate climbs dramatically. At this pace, the entire ring system could be gone in less than 100 million years, possibly much sooner. 100 million years sounds like a long time. It is not on the scale of the solar system. Saturn is 4.5 billion years old. 100 million years is roughly 2% of its total lifespan. We are not watching a permanent feature of the outer solar system. We are watching a brief, shimmering moment. A window that opened recently, probably within the age of the dinosaurs, and will close permanently, long before the sun exhausts itself. Future civilizations, if they exist and look up, will see a plain-banded gas giant, anonymous, ordinary, indistinguishable from a slightly smaller Jupiter. The rings will be a memory, a footnote, a shape preserved only in old astronomical records. We are lucky to be alive right now, lucky to exist in the narrow slice of cosmic time when Saturn wears its crown. That thought is worth sitting with. The rings are young, the rings are dying, and the gap between those two facts is the window we happen to occupy. It is not an accident that this feels significant. It is significant. We are witnessing something that did not exist 100 million years ago, and will not exist 100 million years from now, and we have just barely developed the instruments to understand what we are seeing. The rings are a crime scene, and they are a clock. And both of those facts point toward the same deeper question. What else about Saturn is stranger than it looks? That question answers itself when you turn the planet slightly and look down at its north pole. The rings are the thing everyone sees. Beautiful, iconic, impossible to mistake. But they are not the strangest thing about Saturn. At the top of this world, hidden from Earth-based telescopes for decades, something exists that has no business existing. A shape that belongs in a geometry textbook, not in a churning atmosphere of hydrogen and helium. A hexagon, not a vague, hexagonal-looking smear, not an approximation. A precise, six-sided polygon, centered almost perfectly on the pole, its edges sharp and its angles clean, embedded in a planet that never stops moving. In 1981, NASA's Voyager spacecraft flew past Saturn and photographed its north pole. The images came back, were catalogued, and were largely set aside. It took 6 more years before anyone noticed what was in them. In 1987, an astronomer named David Godfrey was piecing together Voyager data when he found it. Each side of the hexagon runs roughly 9,000 miles long. That is longer than Earth's entire diameter. The full structure spans about 18,000 miles from corner to corner. You could place 2 Earths side by side inside it and still have room. The picture did not hold. Atmospheres do not do this. They swirl. They eddy. They pull structure apart, not together. Straight lines and sharp angles are the language of crystals and mathematics, not gas dynamics. When Godfrey published his finding, many scientists assumed some kind of imaging artifact, a calibration error, anything other than what it appeared to be. Then Cassini arrived at Saturn in 2004. Its north pole was locked in winter darkness, invisible to ordinary cameras. But Cassini carried a visual and infrared mapping spectrometer, and that instrument pierced the dark. The hexagon was still there. 25 years after Voyager, the structure had barely changed. Same shape, same position, same rotational period. Not a trick of imaging, not an artifact. Real. What it is, at its most basic. A vast jet stream of atmospheric gases, moving at roughly 300 miles per hour, locked into a hexagonal path. It rotates with a period of 10 hours, 39 minutes, and 24 seconds. That number matters. It is almost exactly Saturn's internal rotation period, the spin rate of the planet's deep interior. The hexagon does not drift. It does not wander across the pole with the seasons. It is anchored to the planet itself, spinning with it like a feature carved into the atmosphere's bedrock. At the hexagon's center sits a massive polar cyclone. Its eye is so distinct, it resembles a terrestrial hurricane photographed from space. The cyclone is roughly 50 times the size of a typical Earth hurricane. Winds within it exceed 300 miles per hour. Unlike hurricanes on Earth, which form over warm oceans and weaken over land, this storm has no ocean to feed it and no land to stop it. It simply spins, year after year, decade after decade, possibly for centuries. Inside the hexagon, smaller vortices dot the interior, some spinning clockwise and some counterclockwise. The largest of them is roughly 2,200 miles across, about twice the size of the biggest hurricane ever recorded on Earth. They are swept along the hexagonal jet stream like boats caught in a current, racing around the pole in an endless circuit. Between 2012 and 2016, Cassini watched the hexagon change color. When first captured in visible light, it was a deep, striking blue. By the end of the mission, it had shifted to gold. Scientists link this to Saturn's seasons. As the North Pole tilted toward the sun and summer arrived, ultraviolet radiation produced photochemical haze, accumulating in the atmosphere and giving the hexagon its warm golden hue. The center of the polar cyclone, however, stayed blue. Different chemical processes, different airflow, the same geometric structure expressing two different atmospheric personalities at once. But the biggest surprise had not yet arrived. In 2018, Lee Fletcher of the University of Leicester published a study in Nature Communications. His team had been analyzing data from Cassini's composite infrared spectrometer, and they had found something that forced a complete rethinking of what the hexagon actually is. As the northern hemisphere warmed into summer, a stratospheric vortex formed high above the cloud-level hexagon. That upper atmosphere vortex was also hexagonal, not a coincidence, not a separate phenomenon. The hexagon was not a shallow cloud-top pattern at all. It was a towering column of structured atmosphere spanning more than 300 kilometers in height, rising from the troposphere up through the stratosphere. A Rossby wave, a large-scale atmospheric wave driven by the planet's rotation, appeared to be punching upward through layer after layer of atmosphere, imposing its geometric discipline on air masses hundreds of miles above the visible cloud deck. Nothing like this had ever been observed on any other planet. Not shallow, not a surface feature, a column. The natural comparison is Jupiter. The Juno spacecraft revealed that Jupiter's North Pole hosts 9 cyclones, 8 arranged in a ring around a central ninth, like a pattern of swirling cinnamon rolls. No hexagon, no geometric structure, just storms jostling for position. Why does Saturn have a hexagon and Jupiter a chaotic cluster? In 2026, researchers at MIT, GC, and Wanying Kang proposed that the critical variable is the size and speed of the central polar vortex. On Jupiter, the polar cyclone is relatively small and fast, which allows multiple secondary vortices to form around it in a polygonal arrangement. On Saturn, the polar cyclone is larger and its winds slower, which prevents multiple secondary vortices from forming, but instead supports a single meandering jet stream that locks into a hexagonal wave pattern through a process called barotropic instability, a kind of wave that emerges when layers of fluid moving at different speeds begin to interact and amplify each other. A separate experiment at Oxford, conducted by physicists Ana Claudia Barbosa Aguiar and Peter Reed, produced its own answer. They placed liquid in a circular tank and rotated the center and the edges at different speeds. The shear zone between the two fluid bodies stopped being circular as the speed difference grew. It began forming polygons, triangles, squares, pentagons, hexagons. The number of sides depended on the ratio of rotation speeds. When the ratio matched the estimated conditions for Saturn's north polar jet stream, the result was a hexagon. Wait, that seems to solve it. But look at what the Oxford experiment actually produced. The laboratory hexagons were unstable. They required specific, carefully controlled boundary conditions to persist. Change the speed ratio slightly, and the hexagon dissolved into a pentagon or a heptagon. In the lab, maintaining a hexagon for more than a few minutes required constant attention. Saturn's hexagon has held its shape for at least 45 years, likely much longer, possibly centuries. The lab experiment did not make the mystery smaller, it made it larger. A 2020 study in the Proceedings of the National Academy of Sciences by Harvard University researchers proposed the missing piece lies far below anything Cassini could see. Saturn's hexagonal jet stream is not a weather phenomenon in the usual sense. It is driven by convection currents rising from thousands of kilometers below the cloud tops, powered by the planet's internal heat. These deep convective forces create and maintain the great zonal jets, the alternating bands of east and west wind that circle Saturn at every latitude. The hexagonal jet at 78 degrees north is one of these deep jets, locked into its geometric path by the interaction between its own eastward flow and surrounding atmospheric vortices acting as stabilizing anchors. The hexagon may not be a surface oddity, it may be a window into the deep interior of Saturn itself, the internal machinery of the planet stamping its signature onto the visible cloud deck. Now consider where else this shape appears. Honeycomb cells, the basalt columns of the Giant's Causeway in Northern Ireland, the crystal structure of snowflakes, the compound eyes of insects. In each case, the hexagon emerges because it is the most efficient way to tile a surface with equal-sized cells, enclosing maximum area with minimum perimeter. It is nature's preferred geometry when efficiency and stability are the goals. Biology finds it, chemistry finds it, physics finds it. And here, at the North Pole of a gas giant 900 million miles from Earth, the same geometry appears. Not in crystal, not in biology, in wind. There is something almost sacred about it. This shape written into the planet by nothing more than rotation and flow. And yet Saturn's south pole has no hexagon. Just a massive cyclone swirling without geometric structure. Its winds fierce and its boundary entirely circular. The asymmetry between the two poles remains an active area of research. Whatever is driving the hexagon, whether deep convection, barotropic instability, or something not yet fully articulated, it operates differently below each hemisphere, or the hemispheres receive it differently, and we do not yet know why. We can measure the hexagon. We can track its color as it shifts with the seasons. We can map the column rising hundreds of kilometers above the cloud deck, and find it still geometric at every altitude. What we cannot do is fully explain how a turbulent atmosphere sustains the precise conditions for a geometric wave pattern across decades, possibly centuries, of planetary time. The question that follows from all of this is not an easy one. Can we ever truly understand a planet whose atmosphere encodes mathematics into weather? That question will stay open. But the hexagon is only one face of the planet's polar complexity. Inside the storms, and above them, and threading through the entire atmosphere, are dynamics even more violent than anything geometry can describe. The hexagon suggests a planet of impossible order. It is worth waiting a few decades to see what that order is holding down. Most of the time, Saturn looks calm. Pale gold and butterscotch stripes wrap the planet in horizontal layers. Each band is a jet stream, moving at its own speed and its own latitude, sweeping around the planet in parallel rivers of gas. Compared to Jupiter, with its raging great red spot churning for centuries, Saturn appears almost serene, orderly, contained. That serenity is a lie. Roughly once every 20 to 30 years, something detonates inside Saturn's atmosphere. A massive upwelling of warm, moist air punches through the upper cloud deck and erupts into a brilliant white spot, shocking against the planet's muted tones. Within days, the spot grows. Within weeks, it stretches. Within months, it has encircled the entire planet, a belt of churning white cloud and violent electrical discharge that can persist for the better part of a year. These are the great white spots, the most powerful storms in the solar system, unique to Saturn. 6 of them have been observed since 1876. The first was spotted by Asaph Hall, the American astronomer better known for discovering the moons of Mars. Hall used the bright spot to calculate Saturn's rotation period. In 1933, a second was observed by Will Hay, a British comic actor and amateur astronomer who happened to turn his telescope towards Saturn at the right moment and found a planet in upheaval. The 1960 event appeared at high northern latitudes. The 1990 storm erupted near the equator and was tracked by ground-based telescopes and the Hubble Space Telescope. Each of them enormous, each of them temporary, each of them arriving on a schedule that no one could quite predict. Then, in December 2010, the sixth erupted, and this time, Cassini was watching. The storm began as a small white cloud, roughly 800 miles across at about 32 degrees north latitude. A compact disturbance, unremarkable at first glance, but within 3 weeks, it had grown to 10,000 miles from north to south and 17,000 miles from east to west. An equivalent storm on Earth would blanket most of North America from top to bottom. Then Saturn's powerful zonal winds began to shear the cloud. A tail streamed eastward, lengthening day by day as different latitudes moved at different speeds, stretching the storm into a colossal arc. 12 weeks after the eruption began, the tail had wrapped completely around the planet, and then the head of the storm met its own tail. When the two ends collided, the storm's convective activity, the deep upwelling that had driven the whole event, weakened rapidly and ceased within about 50 days. The storm had strangled itself on its own circumference. The atmospheric disturbance it left behind persisted for years, but the engine was gone. But there was more to it. What Cassini revealed was not merely a large weather system. The storm was a three-dimensional monster. Its convective towers, columns of rising warm air driven upward by heat and moisture, extended 10 to 20 times higher than a typical thunderstorm on Earth. Freshwater ice, ammonia ice, and ammonium hydrosulfide particles were carried from deep inside the atmosphere to the visible cloud tops, and that upwelling was what gave the storm its brilliant white appearance. Cassini's visual and infrared mapping spectrometer analyzed the cloud particles and found them to be roughly 55% ammonia ice, 22% water ice, and 23% ammonium hydrosulfide. That last number mattered more than the others. The presence of water ice was the first direct detection of water ice inside a Saturnian storm. It confirmed that the upwelling was drawing material from deep atmospheric layers, from levels where temperatures are cold enough for water to condense and freeze. The storm was not a surface feature. It was a window punched down into Saturn's interior. And the lightning it produced was unlike anything the solar system had shown us before. Cassini's radio and plasma wave science instrument detected what scientists call Saturn electrostatic discharges, or SEDs, rapid bursts of radio frequency energy generated by lightning strikes. During previous smaller storms in Saturn's so-called storm alley, a southern hemisphere latitude band with recurring smaller convective events observed since 2004, SEDs were detectable but modest. The 2010 Great White Spot was something else entirely. At the storm's peak, lightning flashed more than 10 times per second. Each flash released energy roughly 10,000 times greater than a typical bolt on Earth. The storm's total power output was estimated at around 10 to the power of 17 watts. A single storm pumping out energy comparable to a significant fraction of everything Saturn radiates into space. Translated into the radio frequencies Cassini could hear, the lightning sounded like a crackling, hissing roar. It continued, without pause, for months. The question that storm raised was not simply what it was. The question was why it happened so rarely. Jupiter is the famously stormy planet. Jupiter has the Great Red Spot, a storm that has persisted for centuries, surrounded by dozens of smaller storms churning in permanent formation. If you wanted to point to the volatile giant, you would point at Jupiter. Saturn, by comparison, explodes once a generation, and then goes quiet. Not less violent, more patient. The explanation came in 2015, when Chung Lee and Andrew Ingersoll of the California Institute of Technology published a paper in Nature Geoscience. Their answer lay in the behavior of water vapor inside a hydrogen-helium atmosphere. Deep inside Saturn, water exists as vapor, mixed in with the surrounding hydrogen and helium. Moving upward, temperatures drop, and the water vapor rains out. But here is the key. Water vapor is heavier than hydrogen and helium. As the upper atmospheric layers lose their heaviest component, they become lighter, less dense. This creates a situation where the upper atmosphere is less dense than the layers below it. That is not a normal configuration. In a normal atmosphere, denser air sinks and lighter air rises. driving continuous convection. But in Saturn's upper atmosphere, the lighter layer sits on top of the denser layer and acts like a lid. Convection is blocked. The warmer, moister air below cannot rise. Storms cannot form. The atmosphere stabilizes. But the cooling does not stop. The upper atmosphere keeps radiating heat into space. Slowly, over decades, it gets colder and colder. The density inversion weakens, and eventually the cooling overcomes it. The upper layer becomes dense enough, cold enough, that the lid breaks. Warm, moist air erupts upward in a massive convective burst. Water condenses. Ice forms. Lightning crackles. A great white spot is born. Then the eruption releases so much energy and so much moisture that it re-establishes the density inversion. The lid closes again. Saturn waits another 20 to 30 years, cooling slowly, building pressure until the next eruption. Saturn bottles up its energy and releases it all at once. Jupiter leaks it steadily. Lee and Ingersoll proposed that Jupiter lacks great white spots because its atmosphere contains less water vapor. Without enough water to create a strong density inversion, Jupiter's convection is never fully suppressed. Jupiter's constant storms are a sign of release, not power. Saturn's long silence is a sign of accumulation. The 2010 storm also reached upward into layers of Saturn's atmosphere that storms do not typically touch. As the convective towers pump material skyward, two warm air masses formed high above the storm, like blisters of heated gas rising through the stratosphere. Cassini's composite infrared spectrometer tracked them as they drifted around the planet. In early 2012, the two masses merged. The resulting temperature spike was extraordinary. Temperatures in the merged region, which scientists called the beacon, rose by more than 80 Kelvin, making it the warmest point ever recorded in Saturn's stratosphere. Along with the heat came an unexpected chemical signature. Ethylene, a simple hydrocarbon not typically abundant in that part of the atmosphere, appeared in unusually high concentrations. A storm born in the deep troposphere had disrupted the stratosphere hundreds of kilometers above. Saturn's weather is not a set of separate layers. It is a connected system spanning an enormous range of depth and altitude, and a single superstorm can reach through all of it at once. Great white spots occur roughly once per Saturnian year, and one Saturnian year is about 29.5 Earth years. They tend to appear when Saturn's northern hemisphere is most tilted toward the Sun, which suggests a seasonal component, though exactly how sunlight triggers a process unfolding thousands of kilometers below the cloud tops remains uncertain. By historical pattern, the next great white spot could appear sometime in the late 2030s, but the 2010 storm broke the pattern in other ways. It erupted earlier than expected. It appeared at a latitude that did not match the typical progression, and it may have left Saturn in a weakened state. In 2018, ground-based telescopes detected a cluster of 4 mid-sized storms near Saturn's North Pole, each several thousand kilometers across. Some scientists interpreted these as a failed great white spot, a partial eruption that lacked enough energy to build into a full planetary event. If that interpretation is correct, the 2010 storm drained so much from the atmosphere's accumulated reserves that the next cycle could not complete. The planet was still recovering, still recharging. That is the Saturn we live alongside, not the calm, banded world it appears to be on a quiet night. A world that stores energy for decades, then unleashes it in a single catastrophic event. A world where silence does not mean peace, it means pressure is building. The storms come from the atmosphere. But what the atmosphere is doing, at every moment, even between the great eruptions, is shaped by forces that reach far deeper than the visible clouds. And what drives those deeper forces is the structure of something we have not yet looked at directly. Those deeper forces reach far beyond Saturn itself. Nearly 1 billion miles from the Sun, orbiting inside a system we have spent 7 sections exploring. There is a moon, and what is happening on that moon should not be possible. Leave the storms behind, travel outward through the ring system, past the icy moons tumbling in their orbits, and you arrive at Saturn's largest satellite. Scientists call it Earth's evil twin. Not a twin in temperature, not a twin in hospitality. A twin in process, in weather, in landscape, in the fundamental machinery of a world with an atmosphere, with rain, with rivers, with lakes and seas. Except here the rain is liquid methane. The rivers are liquid methane. The seas are liquid methane and ethane. And the surface temperature is roughly 179 degrees Celsius. A moon at those temperatures should be a frozen, static, dead world. It is not. Before Cassini arrived, Titan was a locked box. We knew it was large, about 500 kilometers across, bigger than the planet Mercury. We knew it had a dense atmosphere, the only moon in the solar system with a substantial one, composed primarily of nitrogen, with a surface pressure about 1.5 times Earth's. We knew methane was present, and we knew almost nothing else. The reason was the smog. Titan's upper atmosphere produces a thick photochemical haze that is completely opaque to visible light. Point a telescope at Titan, and you see nothing but a featureless orange sphere. Titan was a mystery wrapped in orange haze. Whatever was happening beneath that haze, we could not see it. Cassini carried tools that could pierce it. Radar, sending radio pulses down through the atmosphere and reading the echoes, and infrared cameras tuned to wavelengths the haze could not block. And riding along with Cassini was a second spacecraft, the Huygens probe, built by the European Space Agency for a single purpose: drop through Titan's atmosphere, measure everything on the way down, land. On 14th January 2005, Huygens separated from Cassini and fell. For 2.5 hours it descended through orange sky, buffeted by winds at different altitudes, slowed by parachutes, sampling the atmosphere continuously and relaying data to Cassini above and then to Earth. This was the first landing in the outer solar system. No instrument had ever rested on a surface this far from the Sun. That is when the pattern broke. The descent images did not show a dead, frozen landscape. They showed drainage channels carved into elevated terrain and branching downslope like river systems flowing toward dark, flat lowlands. They showed rounded pebbles at the landing site, smooth-edged, the way rocks become smooth when liquid flows over them repeatedly over long periods. And when Huygens touched down, its instruments detected that the ground was damp, not wet with water, wet with hydrocarbons. Methane was doing on Titan exactly what water does on Earth, evaporating from the surface, rising through the atmosphere, condensing into clouds, falling as rain, collecting on the ground, flowing across the surface in rivers, pooling in low-lying areas. The cycle was identical in structure to the hydrological cycle that drives weather and shapes landscapes on Earth. The chemistry was completely alien. Over the following 13 years, Cassini completed more than 100 targeted flybys of Titan, mapping the surface in extraordinary detail. At the equator, vast fields of dunes stretch for hundreds of miles, sculpted by wind into parallel ridges that look strikingly like the sand seas of the Sahara or the Namib. But these are not silicate sand dunes. They are made of complex organic molecules called tholins, compounds produced by photochemistry high in Titan's upper atmosphere, slowly settling to the surface like a fine dark snow. Layer by layer, over geologic time, they have built dune fields covering a significant fraction of Titan's equatorial belt. Near the poles, the radar data revealed something that scientists had theorized for decades but never confirmed. Lakes, seas, dozens of them in the northern hemisphere, only one in the south. The largest, Kraken Mare, covers roughly 400,000 square kilometers, larger than the Caspian Sea on Earth. Ligea Mare, the second largest, was probed by radar and found to have depths exceeding 160 meters. The radar also detected the sea bottom, covered in a sludge of heavy organic compounds that fall from the atmosphere, partially dissolve in the liquid methane, and settle to the floor. The smaller lakes perched on elevated terrain, which puzzled scientists at first, turned out to be fed by subsurface reservoirs, a hydrocarbon aquifer that saturates the bedrock and surfaces at certain points, exactly the way springs and seeps work on Earth. Rain falls differently there. Earth's atmosphere can hold roughly 2 centimeters of precipitable water before rain begins. Titan's atmosphere can hold the equivalent of 10 meters of methane before precipitation forms. So Titan's weather does not rain gently and regularly the way a temperate climate does. It accumulates, it holds, and then it releases. Cassini observed equatorial rainstorms exactly once in its entire 13-year mission, in 2009. When rain comes to Titan, it comes in torrents, meters of liquid methane falling from the sky at once, carving flash floods through the organic dunes and filling dry lake beds in a single event. Ralph Lorenz of the Johns Hopkins University Applied Physics Laboratory calculated that Titan's surface contains hundreds of times more liquid hydrocarbons than all the known oil and natural gas reserves on Earth. Titan is quite literally a world swimming in fuel. But the question Titan raises is not about fuel. It is about something much older and much harder to answer. On Earth, life requires liquid water. Every organism we know uses water as the solvent in which biochemical reactions occur. Titan has no liquid water on its surface. Water exists there only as rock-hard ice, a geological material, not a biological one. But Titan has liquid. Methane and ethane flow across its surface and fill its seas. The question is whether that is enough. In 2005, astrobiologists Christopher McKay and Heather Smith proposed a thought experiment. What if organisms on Titan consumed hydrogen from the atmosphere and reacted it with acetylene instead of glucose, producing methane as a waste product instead of carbon dioxide? Such organisms would be methanogens, using the same fundamental metabolic logic as certain archaea on Earth, but adapted to a completely different chemistry. McKay and Smith made a specific prediction. If such life existed in significant quantities, it would measurably deplete hydrogen and acetylene near Titan's surface. In 2010, Darrell Strobel of Johns Hopkins analyzed Cassini data. What he found matched that prediction. Hydrogen appeared to be flowing downward from the upper atmosphere and disappearing near the surface at a rate chemical models could not easily explain. Acetylene, which should be abundant on the surface as a product of atmospheric chemistry, was present in concentrations far lower than expected. The data fit the profile of a biosphere too neatly to be ignored. This is not proof of life. Non-biological explanations exist. An unknown catalytic surface process could be consuming the hydrogen. The acetylene might be trapped in subsurface reservoirs or chemically bound to surface materials. The anomalies are real. Their cause is not established. The data is provocative. It is not conclusive. Then, in 2015, researchers at Cornell University proposed a theoretical cell membrane that could function in liquid methane. They called it an azotosome. It would be built from nitrogen-containing organic molecules called acrylonitrile, not the phospholipid membranes that Earth life uses, which require water to maintain their structure. Unlike Earth's membranes, azotosomes could self-assemble and hold together in liquid methane at Titan's surface temperatures. And acrylonitrile is not hypothetical. Cassini detected it in Titan's atmosphere, and measurements from the Atacama Large Millimeter Array later confirmed it is present in substantial quantities. The raw material is there. In 2025, Christian Mayer and Connor Nixon proposed a mechanism by which small mist droplets interacting with the surface of methane lakes could overcome the chemical barriers to forming these exotic membranes, a potential pathway from simple chemistry to organized structure. Whether life exists on Titan is one of the great open questions in science. The chemistry is permissive, the anomalies are unexplained, and the distance that has made Titan so difficult to study is the same distance that has kept it hidden from us for so long. A mission is coming. Dragonfly, a NASA rotorcraft lander scheduled to arrive in the 2030s, will fly from site to site across Titan's surface, covering more ground than any planetary rover in history. It will be powered by the radioactive decay of plutonium, because solar panels are useless in an environment so cold and dim. It will sample the organic chemistry directly, search for biosignatures, and send back data from a world we can currently only read through radar echoes and infrared signals. What it finds will either deepen the mystery or begin to resolve it. Either way, something else about Titan is already unresolved, and it is more fundamental than life. The methane cycle that makes all of this possible, the rain, the rivers, the seas, the dunes, the chemistry, depends on methane being present in Titan's atmosphere. Photolysis, the process by which sunlight breaks methane molecules apart, is destroying that methane irreversibly. Whether it is being replenished from somewhere below the surface, and whether that replenishment can keep pace, is a question we cannot yet answer. The cycle that makes Titan Earth's twin in process may not be permanent, and that is a thread we will need to return to. Titan hides everything behind an orange veil. The next moon in this story hides nothing at all. It is throwing its interior into the sky. Its name is Enceladus, and almost no one was paying attention to it. That is not surprising. Enceladus is tiny, roughly 300 miles across. You could drive its diameter in a few hours on a highway. In a solar system populated by giants, by Titan with its thick atmosphere and hydrocarbon seas, by the moons of Jupiter with their violent volcanism and buried oceans, Enceladus was easy to overlook. It was just another icy moon in Saturn's crowded court. White, cold, featureless. The textbook said it was geologically dead, too small to hold onto any internal heat, too distant from the sun to be warmed by it. A frozen relic, unchanged since the early solar system. The prevailing wisdom was simple. Small moons run cold. They lose their heat quickly, like a small stone left outside on a winter night versus a large boulder that stays warm for hours. Enceladus had been cold for billions of years. There was nothing left to find. Then, Cassini arrived. In 2005, during one of its first close surveys of Saturn's moons, the spacecraft flew past Enceladus, and its instruments registered something that did not belong. The magnetometer, the sensor measuring Saturn's magnetic field, detected a disturbance near the moon. The field was bending. Something was pushing against it. On Earth, magnetic field disturbances near a body usually mean one thing: an atmosphere, a layer of gas thick enough to interact with a planet's magnetosphere. But Enceladus had no atmosphere. It could not. Its gravity was negligible, barely a fraction of Earth's. Any gas that escaped its surface should have drifted away almost immediately into the vacuum of space. There was nothing to push back against Saturn's magnetic field. Nothing according to every model. Nothing according to the textbook. But the disturbance was real. Cassini looked closer. Its cameras turned toward the south pole of Enceladus, a region that should have been as featureless and frozen as the rest of the moon. What they found rewrote the picture entirely. 4 enormous fractures ran parallel across the south polar surface, each one roughly 135 kilometers long, each one cutting deep into the ice, slicing through it in long, deliberate lines. Scientists named them the Tiger Stripes. And from these fractures, something extraordinary was erupting. Towering plumes of material were shooting hundreds of kilometers above the surface. Jets of water vapor, ice crystals, and organic molecules, rising fast, rising far, moving at roughly 800 miles per hour, fast enough, high enough, to escape the moon's feeble gravitational grip entirely. Not vapor clinging to the surface, not a thin frost, a continuous eruption, venting into space. This was cryovolcanism, cold volcanism, not lava, not molten rock forcing its way through cracks in a silicate crust. This was liquid water, pressurized beneath an ice shell, being driven upward through fractures and blasted into the vacuum of space, where it instantly froze into glittering ice particles. The moon was bleeding into space. Think about what that meant. A body 300 miles across, a body everyone had written off as a frozen relic, had liquid water beneath its surface. It had enough internal heat to keep that water liquid. It had fractures deep enough to reach that water and vent it. And it was doing all of this continuously, relentlessly, with no sign of stopping. Something else was happening. The plumes were not just erupting. They were going somewhere. Scientists had known for decades about Saturn's E-ring, the diffuse outer ring of tiny ice particles that gives Saturn's ring system its faint, wide glow at the edges. It was always puzzling. The E-ring sits outside the Roche limit, the zone where Saturn's tidal forces shred incoming material. Particles in the E-ring should have spread out and dispersed over time. They should have faded. Something had to be replenishing them, but no one knew what. The answer was Enceladus. The plumes from the Tiger Stripes were feeding Saturn's entire E-ring. The ice particles erupted from Enceladus' south pole at high velocity, escaped the moon's gravity, spread along its orbit, and settled into the faint, diffuse ring. Every ice crystal glittering in the E-ring had come from inside that small, white, overlooked moon. Enceladus was not just geologically active, it was actively building one of Saturn's rings. That detail is worth sitting with for a moment. The E-ring had puzzled astronomers for decades. The explanation was sitting inside one of the most overlooked objects in Saturn's entire system. Over the next 12 years, Cassini made more than 20 close flybys of Enceladus, each pass revealing more about this improbable little world. The discoveries did not come all at once. They came in waves, each more startling than the last. The biggest surprises were still ahead. Those waves did not stop at the surface. The plumes were the beginning. What Cassini found in them over the next 12 years arrived in 5 waves, each one built on the last. Together, they turned a tiny overlooked moon into something extraordinary, something that no one had expected to find this far from the sun. The first wave was the ocean itself. During its close passes, Cassini's instruments measured Enceladus's gravity field with great precision. The measurements revealed something subtle, but unmistakable. The moon was slightly deformed. Its mass was not distributed evenly. It was heavier in some places than the surface ice would suggest. Scientists recognized this pattern. It was the signature of a large body of liquid water hidden beneath the crust. Liquid redistributes in ways that solid rock cannot. Then came the libration analysis. Libration is a slight wobble in the rotation of a moon, caused by its gravitational interaction with the planet it orbits. If Enceladus were a solid body, ice and rock locked together all the way down, its wobble would be small and predictable. But when researchers analyzed Cassini's measurements carefully, the wobble was larger than a solid body could produce. The ice shell was not resting on a solid interior, it was floating on a global ocean, a sea of liquid water completely encircling the rocky core, hidden beneath roughly 20 to 25 kilometers of ice. Near the South Pole, where the tiger stripes cut through, the ice may be only a few kilometers thick. Not a subsurface pocket of slush, a global ocean. The second wave came from what the plume material was made of. Cassini's cosmic dust analyzer sampled the ice grains erupting from the tiger stripes and the particles drifting through the E-ring. Inside those grains, it found sodium chloride, table salt, in concentrations comparable to Earth's oceans. The ocean of Enceladus was not pure water. It was a salty, mineral-rich solution, the kind that forms only when water has been in direct contact with rock over long periods, leaching minerals the way seawater interacts with Earth's ocean floor. This mattered enormously. It meant the ocean was not sitting isolated beneath the ice, sealed off from the rock below. It was touching the rocky core, dissolving it slowly, carrying minerals upward. It was a chemically active system, not a sterile pool. The third wave was the strangest, and the most beautiful. Among the ice grains, scientists found nanoscale particles of silica, tiny grains of silicon dioxide between 2 and 8 nanometers in size. That is 8 nanometers. A grain of sand you could not see, could not feel, smaller than most viruses. And yet that grain carried a precise message. On Earth, silica nanoparticles of this specific size form in only one way. Hot water, heated to at least 90 degrees Celsius, rises through rock, dissolving minerals as it goes. When that hot mineral-laden water meets cooler water above, the dissolved silica precipitates out as nanoparticles of exactly this size. This is what happens at hydrothermal vents on Earth's ocean floor, at the mid-ocean ridges, at the black smokers. Hot water emerging from the rocky crust, carrying dissolved minerals into the cooler sea above. The implication was unmistakable. Enceladus has hydrothermal vents. At the bottom of its ocean, right now, hot water is rising through the rocky core and meeting the cooler sea above it. The same geological process that powers some of the most remarkable ecosystems on Earth is operating inside a moon 300 miles wide in the outer solar system. A grain of sand, 8 nanometers across, proved there is hot water on the floor of an alien sea. That was discovery 3 of 5. The fourth was the one that changed everything. On 28 October 2015, Cassini made its deepest dive through the plume, passing just 49 kilometers above the surface. Its ion and neutral mass spectrometer sampled the gas directly, and it found molecular hydrogen in significant quantities. Hunter Waite of the Southwest Research Institute led the analysis, published in Science in April 2017. His conclusion was that the most plausible source was serpentinization, an ongoing hydrothermal reaction between water and iron and magnesium-rich rock. When water reacts with those minerals, it produces serpentine and releases hydrogen gas as a byproduct. The answer was stranger than expected. Because the hydrogen was not just a chemical curiosity, it was an energy source. On Earth, microorganisms called methanogens use hydrogen to reduce carbon dioxide into methane, extracting energy from a purely chemical reaction. No sunlight, no photosynthesis, just rock and water, reacting, releasing energy that biology can use. These organisms form the base of entire ecosystems in the deep ocean, thriving in complete darkness, powered entirely by the chemistry happening around the vents. Enceladus had liquid water, it had hydrothermal vents, and now it had the chemical energy gradient that life on Earth is already known to exploit. Not theoretically, not in some distant hypothetical future. Right now, today, hydrogen is being produced in the ocean of Enceladus. The fifth wave came in two parts, years apart. In 2018, Frank Postberg of the University of Heidelberg and colleagues published a study in Nature reporting the detection of large, complex organic molecules in the plume, molecules with molecular weights above 200 atomic mass units. Not simple methane, not small building blocks. These were fragments of much larger structures, possibly including nitrogen and oxygen-bearing compounds, the kinds of molecules associated with prebiotic chemistry, with the raw ingredients life uses to build itself. Then, in 2023, researchers identified phosphates in the plume grains: carbon, hydrogen, nitrogen, oxygen, phosphorus. 5 of the 6 elements essential for life as we know it, confirmed in material that came directly from Enceladus's ocean. Only sulfur remains undetected, and many scientists consider its presence likely given the geochemistry involved. A 2025 reanalysis of Cassini data from its highest speed flyby found the chemistry even richer. Aliphatic compounds, cyclic esters, ethers, and tentatively nitrogen and oxygen-bearing molecules in freshly ejected grains. The ocean of Enceladus was not a sterile pool of salt water. It was a chemically dynamic, reactive environment undergoing exactly the kinds of processes that on Earth are intimately connected to biology. Now, consider the time question. Hydrothermal activity on Enceladus appears to have been ongoing for at least 40 million years, possibly more than 100 million. On Earth, the earliest evidence of life appears roughly 500 million years after the planet's formation. Morgan Cable of NASA's Jet Propulsion Laboratory put it plainly. If you have all the ingredients for life but no life yet, wait about 10 million years and you should have life. Enceladus has been running those ingredients, that chemistry, that heat, for at least 4 times that long. All the ingredients appear to be there. The question is life there? We do not know, and Cassini could not tell us. Not because it failed to look, but because it was never built to ask that question. Cassini launched in 1997, years before anyone knew Enceladus had a plume, an ocean, or a hydrothermal system. Its instruments were designed for a different era of planetary science, for mapping, for atmosphere sampling, for gravity measurements. Detecting biosignatures requires a different kind of instrument entirely. Tools designed to identify amino acid patterns, protein structures, lipid membranes, metabolic byproducts. Those instruments did not exist when Cassini was built. It raised the question, but it could not answer it. The next step is to go back, to fly through the plume again with instruments designed specifically to search for signs of life. Chris Glein of the Southwest Research Institute described it simply: going fishing, but in a very methodical manner. And this is where something remarkable becomes clear. Reaching a subsurface ocean sounds impossibly difficult, miles of ice, no way to drill down, no way to reach the water. But Enceladus does not ask you to drill. It is already spraying its ocean into space. The tiger stripes are open fractures leading directly to the sea below. The plume carries that sea into vacuum, where a spacecraft can simply fly through it and collect what is there. You do not need to land. You do not need to drill. You just need to fly through the spray. This is why Enceladus may be the best place in the solar system to search for extraterrestrial life. Better than Mars, where liquid water existed billions of years ago, but appears to be largely gone now. Better than Europa, Jupiter's ocean moon, where scientists also suspect a deep liquid ocean, but where there is no plume to sample easily, no open window to the water below. Enceladus is offering its ocean to us, shooting it into space, begging to be studied. No other world in the solar system does this. There is one more thing worth noting quietly. This heat, this ocean, this extraordinary chemistry does not come from nothing. It comes from tidal interaction, from the gravitational squeeze Saturn applies as Enceladus moves in its orbit, an interaction shaped by its resonance with other moons. That resonance has been running for tens of millions of years. It is running right now. What would happen if it stopped is a question the data does not yet answer. Everything we have found out here orbits at one thing: the plumes, the seas, the rings, the hexagon, the storms, the moons offering their oceans to the sky. All of it circles a single vast body that we have studied for centuries and never once touched on the inside. It is time to fall into it. Imagine you could. Imagine descending into Saturn, not orbiting it, not skimming its cloud tops, but falling straight down. You would enter at the top of the atmosphere where the temperature is roughly negative 178 degrees Celsius, and the pressure is about 1 bar. That is the same pressure as sea level on Earth. It would feel, in that sense, almost familiar. Above you, the sky would be a pale gold haze. Ammonia ice crystals would drift past you. The banded cloud layers, each moving at a slightly different speed, would stretch to every horizon without interruption, and you would fall. Within a few hundred kilometers, the temperature would begin to rise, the pressure would climb. The ammonia clouds would give way to a different chemistry. Ammonium hydrosulfide clouds, then water ice clouds forming in the warmer layers below. The sky would darken. The photochemical haze that scatters sunlight in the upper atmosphere would thin out, and eventually, the last trace of light would disappear. Past a certain depth, there is no light at all. Just heat, just pressure, just the thickening density of hydrogen surrounding you on every side. Here is what you would expect to happen next. You would expect to hit something. A surface, a shoreline, the boundary between atmosphere and whatever lies beneath it. Every instinct built by living on a rocky planet says there has to be a floor somewhere. There is no floor. At roughly 1,000 kilometers below the cloud tops, the temperature reaches about 1,000 Kelvin, and the pressure climbs to roughly 1,000 bars. At those conditions, hydrogen is no longer a gas, it becomes a liquid, but you would not crash into an ocean. The gas does not stop being a gas and suddenly become something else. It thickens, gradually, imperceptibly. The density increases so smoothly that you would find yourself swimming in liquid hydrogen without ever having crossed a line. No surface, no shoreline, no edge, just a gradient, a smooth increase in density that turns atmosphere into ocean without announcement. Saturn has no surface to land on. It has never had one. But the descent is not finished. Keep falling. Deeper still, at roughly half the distance from the cloud tops to the center of the planet, the pressure reaches approximately 2 million bars, 2 megabars, and the temperature climbs to around 6,000 Kelvin, roughly the temperature of the surface of the sun. Here, something happens that has no equivalent anywhere in ordinary experience. In the outer layers, hydrogen exists as molecules, 2 atoms bonded together, behaving like the light gas we use to fill balloons, the gas that burns. But at 2 megabars, the pressure is so extreme that those molecular bonds break entirely. The electrons are stripped from their atoms. They become free to move through the material, no longer bound to any particular nucleus. The hydrogen becomes metallic. It conducts electricity. It reflects light, though there is no light here to reflect. It behaves not like a gas or a familiar liquid, but like a liquid metal, something resembling molten lithium or sodium, flowing and conducting in the dark. This is not a phase transition scientists have observed by cooling something down or heating something up. It is pressure alone that does it. Pressure so great that matter itself stops behaving by its usual rules. And that transition is the reason Saturn has a magnetic field at all. The metallic hydrogen layer is not sitting still. Convection currents move through it, slow churning motions driven by the temperature difference between the deep interior and the layers above. A conducting fluid in motion generates a magnetic field. The same principle behind the dynamo in Saturn's core, in Earth's core, in the engines of every magnetic planet in the solar system. Saturn's metallic hydrogen layer, conducting electricity while being stirred by convection, acts as a dynamo generating a field that extends far beyond the planet, shaping the paths of charged particles, influencing the orbits of ring particles, building the invisible architecture of the magnetosphere. Then the data shifted. Saturn's magnetic field is almost perfectly symmetric. On Earth, the magnetic poles are offset from the geographic poles by roughly 11 degrees. On Jupiter, the offset is about 10 degrees. On Saturn, the offset is essentially 0. The field is aligned with the rotation axis with a precision that appears unique in the solar system. This seems like elegant tidiness. It is not. Dynamo theory says a perfectly symmetric magnetic field should not be stable. It should wobble. It should tilt. It should drift over time. The fact that Saturn's field remains so perfectly aligned suggests something is actively smoothing it out. Something is absorbing the asymmetries before they can reach the surface. That something is helium. Deep inside Saturn, under the pressure and temperature conditions found between the metallic hydrogen dynamo region and the outer molecular envelope, helium becomes insoluble in hydrogen. Under ordinary conditions, helium and hydrogen mix freely. Down here, they do not. The helium separates from the hydrogen like oil separating from water. It condenses into droplets, and those droplets, being denser than the surrounding metallic hydrogen, fall. They rain downward through the interior, settling toward the center of the planet. This thick layer of helium rain sits between the dynamo and the outer atmosphere, and according to modeling by Sabine Stanley at Johns Hopkins University, it acts as a filter, absorbing asymmetries in the magnetic field before they propagate outward, presenting a deceptively smooth, symmetric face to the outside universe. Helium rain was first proposed theoretically in the 1970s by David Stevenson, then at the California Institute of Technology. He was not trying to explain the magnetic field, he was trying to explain something else. Saturn is too bright. Saturn radiates roughly 2.5 times more energy into space than it receives from the Sun. Jupiter does this too. Jupiter's excess heat can be explained by slow cooling. Jupiter formed hot, and a planet that large retains its heat for a long time. Saturn, being smaller, should have cooled faster. It should no longer be radiating excess heat at this rate. Something is providing additional energy from the inside. As helium droplets fall through the interior, they convert gravitational potential energy into heat. The settling of helium is a slow, continuous energy source. It is keeping Saturn warmer than it should be by every other account. And it explains something else. Saturn's atmosphere appears depleted in helium compared to the Sun, and compared to Jupiter. The helium has not vanished. It has sunk. It has hidden itself in the deep interior, invisible to any instrument that can only observe the cloud tops. In 2016, Gilbert Collins and colleagues at Lawrence Livermore National Laboratory provided the first experimental evidence that this actually happens. Working with the Omega laser at the University of Rochester, they compressed a mixture of hydrogen and helium and blasted it with shock waves. At specific thresholds of temperature and pressure, the helium separated from the hydrogen exactly as Stevenson had predicted, 4 decades earlier, at conditions matching what Saturn's interior is expected to produce. The theory was not just elegant, it was right. While the helium falls, something else is falling too. Saturn's atmosphere contains methane, not in enormous quantities, but enough. Methane is one carbon atom bonded to 4 hydrogen atoms. Deep in the atmosphere, where lightning strikes and the temperature soars, methane molecules are broken apart. The carbon is freed. And as that liberated carbon sinks deeper, encountering greater pressures and temperatures with every kilometer it descends, it transforms. First, the carbon atoms link together to form soot. Then, as the pressure continues to climb, the soot is compressed into graphite. And then, deeper still, the graphite is crushed into diamond, crystals of pure carbon, forming in the incandescent dark of a gas giant, falling through layers of liquid metallic hydrogen toward a core that may not even be solid. In 2017, researchers at the SLAC National Accelerator Laboratory used high-powered lasers to recreate the pressure conditions found deep inside giant planets. They demonstrated that carbon does form diamond structures at those extremes. The process is not theoretical, it happens. But the diamonds would not sparkle. There is no light in Saturn's interior. They would form in darkness, fall in darkness, accumulate if they survive the heat and pressure, somewhere in the transition zone between the metallic hydrogen layer and the fuzzy core below. Some models suggest they might eventually melt there, the temperatures near the core becoming too extreme even for diamond, forming a layer of liquid carbon surrounding the center of the planet, a sea of diamond surrounding the center of the planet. Other models suggest they dissolve into the metallic hydrogen, contributing their carbon to the chemistry of the deep interior. We do not know which is true. We do not know for certain. No probe has ever descended past Saturn's cloud tops. No instrument can directly observe conditions below the atmosphere. Everything we know about what lies beneath is inferred. From gravity measurements, from magnetic field observations, from ring seismology, the vibrations that travel outward from the interior and imprint themselves on the inner rings, from atmospheric composition, from laboratory experiments that recreate briefly the pressures of a world we will never touch from the inside. The picture that emerges is extraordinary. A fuzzy core of smeared rock and ice dissolving gradually upward into the surrounding envelope. No sharp boundary between what is core and what is not. A deep layer of metallic hydrogen where helium rains out and diamonds form and fall. A thick outer envelope of molecular hydrogen and helium transitioning seamlessly from liquid to gas. with no surface marking where one ends and the other begins. Saturn should not exist, not in the clean, well-ordered way textbooks describe planets. It is not a solid ball with a gaseous shell. It is a continuous gradient, a planet without a surface, a world where the interior is not a place but a process, a constant churning of elements transforming from one state to another under conditions so extreme that the ordinary categories of solid, liquid, and gas lose their meaning. And that process is not finished. The helium keeps sinking, the diamonds keep falling, the interior is still changing, slowly, steadily, and will keep changing for billions of years to come. Saturn is not a finished thing. It is something still becoming. Rise back out of that dark. Past the metallic hydrogen, past the churning envelope, past the rings, and look around at what else is out here. Saturn has 146 moons, more than any other planet in the solar system. Jupiter has 95, Uranus has 28, Neptune 16, Saturn has 146, and the number keeps growing. As recently as 2023, astronomers discovered dozens more, tiny irregular bodies just a few kilometers across. Most of them captured asteroids or comets snagged by Saturn's gravity during the early chaos of the solar system's reshuffling. Most are unremarkable, small, dark, tumbling on distant tilted orbits that will never produce a headline. But among the 146, several are genuinely strange. Strange in ways that challenge fundamental assumptions. A few of them should not be possible. Start with the smallest. Mimas is the innermost of Saturn's major moons, just under 400 kilometers in diameter, and the smallest object in the solar system known to have pulled itself into a roughly spherical shape under its own gravity. Its surface is ancient and battered, almost entirely covered in impact craters. One crater dominates everything. Herschel crater, named after William Herschel, who discovered Mimas in 1789, is 130 kilometers across. Nearly a third the diameter of the moon itself. The impact nearly shattered Mimas entirely. Had it been slightly larger or slightly faster, there would be no Mimas. Instead, there is a scar so enormous it gives Mimas its famous resemblance to the Death Star. Scientists noticed the resemblance as soon as the first close-up images arrived. It was not lost on them. But the more interesting story is not on the surface. It is inside. In 2024, researchers completed a careful analysis of data collected by the Cassini spacecraft during its years at Saturn. They were looking at Mimas's libration, its wobble, the slight rhythmic oscillation in its rotation as it orbits. And what they found was unexpected. The wobble was too large. Larger than it should be if Mimas were a solid body of ice and rock all the way through. The best explanation was a global internal ocean, liquid water sitting roughly 20 to 30 kilometers beneath the ice. Not a hint of warmth, not a crack, not a plume, but something did not add up. Mimas shows no signs of geological activity whatsoever. No fractures in the surface, no resurfacing, no plumes erupting from the ice. Its ancient, heavily cratered surface looks exactly like a world that has been geologically dead for billions of years. And yet the physics of its wobble demands liquid water inside. If confirmed, Mimas would be the most unlikely ocean world in the solar system. A body that hides its ocean behind the facade of a dead, battered moon. Every other ocean world we know gives itself away somehow. Enceladus has its tiger stripes and its plumes. Europa has its fractured surface. Mimas has nothing. A perfect disguise. The ocean, if it is there, is completely invisible from the outside. That is one puzzle. The next is a different kind of impossible. Hyperion orbits farther out, roughly 270 kilometers across, irregularly shaped, resembling a giant sponge or a broken piece of pumice. Its surface is covered in deep, sharp-edged craters with dark floors, so closely packed and so strangely proportioned that Hyperion looks like it has been eaten from within. The reason is its density. Hyperion is extraordinarily porous, with a density roughly half that of water. The moon is likely a loose rubble pile of ice and empty space, more void than solid material. When meteoroids strike it, they do not excavate. They compress. The porous surface deforms inward, creating deep, sharp-walled pits rather than the broad, shallow craters you see on denser bodies. The dark material at the bottom of each pit is organic, rich debris that has settled into the lowest points. And then there is the rotation. Most moons are tidally locked. They always show the same face to their parent planet, pulled into that orientation by gravity over millions of years. exactly as Earth's moon always faces us. Hyperion does not do this. Hyperion tumbles. Its rotation axis wanders unpredictably from orbit to orbit, driven by the Titan's gravitational influence and Hyperion's own irregular shape. It is one of only a handful of objects in the solar system with confirmed chaotic rotation. Predicting which face Hyperion will show Saturn at any given moment is, in a rigorous mathematical sense, impossible. Not difficult, not uncertain. Impossible. The mathematics of chaos theory applies directly here, and the answer it gives is that the system has no stable, predictable solution over long timescales. A moon whose orientation no one can know in advance. Iapetus is different again. Giovanni Domenico Cassini discovered it in 1671, and it baffled him immediately. The moon was clearly visible when it appeared on one side of Saturn. When it moved to the other side, it vanished. Cassini correctly deduced that one hemisphere must be dramatically brighter than the other. He was right, and he never knew why. Cassini the spacecraft, 3 centuries later, confirmed and finally explained what Cassini the astronomer had observed. Iapetus has a striking two-toned appearance. Its leading hemisphere, the face it presents forward as it orbits, is coated in material as black as coal. Its trailing hemisphere is brilliantly white, as bright as fresh snow. The boundary between them is sharp and dramatic. From space, Iapetus looks like a moon assembled from mismatched halves. The mechanism took centuries to piece together. The dark material is a thin veneer of organic rich dust, swept up from Saturn's outer moon Phoebe, and its associated Phoebe ring, a vast tenuous ring of dark material that orbits Saturn in the opposite direction to most of its moons. As Iapetus orbits, it plows through this dust, accumulating it on its leading hemisphere like a car driving through insects on a summer highway. Once that hemisphere darkens, it absorbs more sunlight and warms slightly. The warming causes ice to sublimate from the dark surface and redeposit on the cooler, brighter trailing hemisphere. A feedback loop that sharpens the contrast over millions of years. Dark gets darker, bright gets brighter. The two-toned face is a consequence of physics and time. But the strangest feature of Iapetus is not its color. It is its shape. Running along its equator is a mountain ridge rising roughly 13 kilometers above the surrounding terrain, comparable to the tallest mountains on Mars. The ridge extends approximately 1,300 kilometers, roughly 3/4 of the way around the moon, and it sits almost perfectly on the equator, like a seam on a tennis ball. On a moon barely 1,500 kilometers in diameter, this ridge has no obvious reason to exist. No one fully understands how it formed. 3 hypotheses have been proposed. Perhaps Iapetus once rotated much faster, and the ridge is a frozen bulge from when centrifugal force pushed material toward the equator, before tidal interactions with Saturn slowed its spin. Perhaps it is the remains of a collapsed ring system that once orbited the moon itself, settling onto the surface along the equatorial plane. Perhaps it is a tectonic compression ridge formed when the interior cooled and contracted. None of these explanations is fully satisfactory. The ridge remains one of the most enigmatic features in the solar system. A mountain range that has no business existing where it does. And it keeps existing, perfectly placed, waiting for an explanation that has not yet arrived. The smaller moons have their own tricks. Pan and Atlas, tiny moons orbiting within and near the edges of the rings, have distinctive flying saucer shapes. Pronounced equatorial ridges give them the look of ravioli. Those ridges formed as ring material accumulated on their equators, grain by grain, over millions of years. The moons are literally wearing skirts of ring particles, built up slowly from the very system they orbit within. Daphnis is just 8 kilometers across, and orbits within the Keeler gap in the A-ring. As it moves, its gravity creates visible waves in the ring material on either side of the gap, ripples propagating outward like the wake of a boat passing through still water. Cassini photographed these waves in extraordinary detail, a moon smaller than a city, carving its signature into the rings with every orbit. Prometheus and Pandora orbit on either side of the thin F-ring. Their gravity confines the ring particles into a narrow band. Without them, the F-ring would spread out and dissipate. They are gravitational herders, maintaining order in a system that would otherwise dissolve into chaos. And then, there is Phoebe, far out from Saturn, on a retrograde orbit moving opposite to the planet's rotation. Phoebe is almost certainly a captured Kuiper Belt object, a relic from the outer reaches of the early solar system, trapped by Saturn's gravity during the chaos described by the NICE model. Its dark, irregular surface and unusual orbit mark it as a visitor that never quite became part of the family. A fossil from the primordial solar system, preserved in Saturn's gravitational embrace. The war that reshuffled the planets left survivors scattered across the solar system. One of them is still out here, orbiting backwards, dark and quiet. Each of these moons tells a different story. Mimas hides an ocean behind a dead surface. Hyperion tumbles with no predictable face to show. Iapetus wears a mask of darkness on one side and carries an inexplicable mountain range on its equator. Pan wears a skirt of ring particles. Daphnis carves waves with every orbit. Phoebe is a refugee from the edge of the solar system. Together they form a system so rich, so diverse, so full of unsolved puzzles that a single spacecraft spent 13 years exploring it and barely scratched the surface. And that spacecraft had one last extraordinary thing left to do. Every discovery in this story came from one machine. The ocean beneath Enceladus's ice, the methane seas of Titan, the hexagonal storm at Saturn's North Pole, the fuzzy, sloshing core at the planet's heart, the young, temporary rings, every one of them. One machine, 13 years, and a death it chose for reasons that say something lasting about the kind of species we are. On 15th October 1997, a Titan IVB rocket lifted off from Cape Canaveral, carrying the heaviest interplanetary probe NASA had ever launched. The spacecraft weighed 6,800 kilograms. Mounted atop it was a smaller craft built by the European Space Agency, designed to separate from the orbiter during the journey and descend to the surface of an alien world. The two were named Cassini and Huygens, after the astronomers who, 3 centuries earlier, had made the first great discoveries about Saturn and its moons. Giovanni Cassini found the gap in the rings. Christian Huygens identified Titan. Now their names rode on machines sent to touch those same places. There is a quiet circularity in that worth holding for a moment. The mission was a collaboration between NASA, the European Space Agency, and the Italian Space Agency, costing roughly $3.2 billion over its lifetime. The orbiter carried 12 scientific instruments. Huygens carried 6 more. Its power came from 73 pounds of plutonium-238, generating electricity through radioactive decay, because at Saturn's distance the sunlight is roughly 1% of what reaches Earth. Solar panels were not an option. The machine that would spend 13 years studying one of the most luminous objects in the outer solar system could not run on its light. Cassini could not fly directly to Saturn. The planet was too far. The spacecraft was too heavy for the rockets available. So mission planners designed one of the most intricate flight paths in the history of spaceflight. 2 gravity-assist flybys of Venus, 1 of Earth, 1 of Jupiter. Each planet's gravity bent the spacecraft's trajectory and added speed, like a stone gaining momentum as it skips from surface to surface. The journey took 6 years and 261 days. Cassini covered roughly 2.2 billion miles before it reached Saturn's neighborhood. Then came the insertion burn. One of the most nerve-wracking moments of the entire mission. Cassini had to fire its main engine for roughly 96 minutes, slowing just enough for Saturn's gravity to capture it. Not too fast, and not too slow. Off by even a fraction, and the spacecraft would sail past the planet into deep space, lost forever. The team on Earth could not intervene in real time. The signal delay meant every correction had already been calculated and loaded. The spacecraft was alone. On 30th June 2004, the burn succeeded. Cassini became the first spacecraft to orbit Saturn. What followed was 13 years of revelation. Cassini discovered the geysers erupting from Enceladus's tiger stripes. It confirmed the global ocean beneath that moon's ice. It detected the hydrothermal vents at the ocean floor and the molecular hydrogen they produced. It found the organic compounds drifting upward through the plumes. It revealed the methane lakes and seas of Titan. It delivered Huygens to Titan's surface on 14 January 2005, making it the first landing ever achieved in the outer solar system. It observed the hexagonal polar vortex in detail no prior mission could match. It watched the 2010 Great White Spot erupt, grow, wrap around the planet, and strangle itself. It measured the mass of the rings with precision that revealed their youth. It discovered new moons. It photographed the rings backlit against the sun and showed structures invisible in any other light. It detected the interior oscillations that proved Saturn's core is not solid, but fuzzy and sloshing. The tally, 294 orbits of Saturn, 162 targeted flybys of Titan, 23 close encounters with Enceladus, nearly 500,000 images, more than 4,000 scientific publications. By any measure, it was the most productive planetary orbiter mission in history. But there was a cruel twist. The mission's greatest achievement was also the reason it had to end in a way no one wanted. By 2017, Cassini had been in space for nearly 20 years. Its hydrazine fuel, used to control trajectory and orientation, was nearly gone. Without fuel, the spacecraft could not be steered. It would eventually drift into an uncontrolled orbit, tumbling without direction, and there was a real possibility it would crash into one of the moons below. Not just any moon, Enceladus or Titan, the two moons Cassini's own discoveries had identified as potentially habitable. Cassini was not a sterile spacecraft. Despite precautions taken during construction, it carried terrestrial microorganisms embedded in its structure and instruments. Microscopic passengers it had carried from Earth for 2 decades. If the spacecraft crashed uncontrolled into Enceladus, those microbes could reach the moon's ocean. And if a future mission then detected life in that ocean, scientists would never know. Was it native? Or was it something Cassini brought with it and seeded there? The scientific integrity of every future search for life in the Saturn system depended on keeping Cassini away from the habitable moons. Not an unremarkable end, drifting slowly into darkness. Deliberate destruction. The spacecraft had to be killed on purpose because the moons it had discovered might harbor life, and the microbes it carried could ruin the answer forever. The solution was, in the words of the mission team, elegant and devastating. Cassini would be directed into Saturn itself. The planet's thick atmosphere would incinerate it like a meteor, destroying it completely, dispersing everything it carried into the hydrogen and helium below. No contamination could reach any moon. This final phase was called the grand finale. After a last close flyby of Titan on 22nd April 2017, Titan's gravity bent Cassini's trajectory one final time, launching it over the rings and into 22 orbits, threading the narrow gap between the innermost ring and Saturn's cloud tops. That gap was roughly 200 miles wide. Cassini passed through it at speeds up to 70,000 miles per hour. Each orbit collected new data: ring particle composition at close range, gravity mapping, magnetometer readings from closer than any prior measurement. During the final 5 orbits, Cassini dipped into Saturn's uppermost atmosphere, skimming through thin gas between roughly 1,000 and 1,060 miles above the cloud tops, thrusters firing continuously to hold the antenna toward Earth. It was tasting Saturn's atmosphere directly for the first time in the mission's history. It was doing new science on the way to its own destruction. On 11 September 2017, Cassini made a distant flyby of Titan that the mission controllers called the goodbye kiss. The gravitational nudge trimmed the orbit one last time, bending its path towards Saturn's atmosphere on 15th September. There would be no more course corrections, no more flybys, no more escapes. In the early morning hours of 15th September 2017, engineers and scientists gathered at NASA's Jet Propulsion Laboratory in Pasadena. Many had worked on Cassini for decades. Some had been involved since the mission's conception in the 1980s. They watched their screens and waited. Cassini entered Saturn's atmosphere, pointed at Earth, antenna transmitting continuously, 7 of its 12 instruments active, collecting measurements of atmospheric composition, temperature, pressure, and magnetic field. It was falling at tens of thousands of miles per hour. As the atmosphere thickened, drag increased. The small thrusters fired harder and harder to hold the antenna toward home. The spacecraft fought to maintain contact. For about a minute, the thrusters held. Then the atmosphere overwhelmed them. Cassini began to tumble. The antenna swung away from Earth. The signal stopped. Wait. The signal had already been gone for 83 minutes before anyone on Earth knew it. That is how long light takes to travel from Saturn to Earth. The spacecraft was already vaporized, already dispersed, already gone, while the scientists in Pasadena were still watching their screens and waiting for silence that had not yet arrived. When it came, the signal went flat at the Deep Space Network receiving station in Canberra, Australia. The transmission that had been streaming for 20 years simply ended. At JPL, there were tears. There was applause. There were colleagues who had spent careers working toward this moment and dreading it in equal measure. Project manager Earl Mays shook hands with project scientist Linda Spilker. The room was quiet for a long moment. then it was not. Cassini was gone, vaporized within seconds of losing contact. Its plutonium, its instruments, its cameras, its memory, all converted to heat and dispersed into the planet it had studied for 13 years. The spacecraft became part of Saturn. The New York Times ran the story on its front page. The Washington Post published an editorial headlined, "The Cassini mission embodies the best of humanity." The hashtag trended worldwide. More than 3 million people visited the mission's website. For a few days, the world paused to mourn a robot and celebrate what it had achieved. Cassini proved that the outer solar system is not a frozen wasteland. It is a dynamic, chemically rich frontier where the conditions for life may exist right now. Not in some ancient past, not on some distant exoplanet, on moons orbiting the 6th planet from our sun, but it also left questions it could not answer, mysteries it uncovered and could not solve. The instruments it carried were designed before anyone knew about Enceladus's ocean, before anyone knew about the plumes, before biosignature detection was the mission's purpose. What Cassini found was more than it was ever built to find, and less than we now know we need. The answers it reached for, it could not quite grasp. Those questions are still open, and they are not going to wait forever. Cassini left its questions behind. It is worth following them forward, all the way forward, to the end. Saturn itself will survive. That is the first thing to understand. A gas giant does not die quickly. It has no surface to erode, no atmosphere to bleed away into space, no internal fire that will exhaust itself and go cold. Saturn will be here long after our civilization is gone, long after our species is gone, long after the Earth itself has been consumed. In roughly 5 billion years, the Sun will exhaust its hydrogen and swell into a red giant, expanding outward until its outer layers reach roughly the orbit of Earth. Mercury and Venus will be swallowed. Earth will likely be destroyed or rendered unrecognizable. Saturn, orbiting at 9.5 astronomical units, will survive that phase intact. It will still be there, cold and intact, orbiting the dim remnant of its star. And yet, it is changing right now. Measurably. Irreversibly. The rings go first. Ring rain is draining ice into Saturn's atmosphere at what NASA describes as the worst-case rate, enough water to fill an Olympic swimming pool every 30 minutes. Cassini measured an even greater flow of material spiraling inward along the equator under gravity and drag. Together, the rings may have less than 100 million years remaining. That is 2% of the time Saturn has already existed. The innermost rings, the D and C rings, will vanish first. The massive B ring will hold out longer, but not forever. The A ring will follow. Eventually, the only ring left will be the E ring, the one fed continuously by the plumes of Enceladus, and even that depends entirely on how long the little moon can sustain its geological activity. Think about what a ringless Saturn would look like. Stripped of the one feature that makes it the most recognizable planet in the solar system, it would still be a gas giant banded in gold and butterscotch, still surrounded by its moons. But it would look like a slightly smaller Jupiter. Anonymous. Ordinary. The beauty that inspired wonder for 400 years. From Galileo's confused sketches to Cassini's high-resolution portraits, would simply be gone, and the loss would be permanent. The conditions that created the rings are unlikely to repeat. The rings are a one-time gift, a transient ornament in the life of a planet, but the change runs deeper than the rings. The interior keeps changing too, in ways that will never be visible from the outside. Helium rain continues, slowly and relentlessly, separating from hydrogen and sinking toward the core. Over time, this changes Saturn's internal structure. The deep interior grows denser. The outer envelope grows lighter. The thermal profile shifts. And the diamonds, if they exist, continue to form and fall in darkness. Carbon drifting downward, and over billions of years, this slow rain of gemstones may build significant carbon deposits deep within the planet. Saturn is not finished becoming what it will be. It is still in motion. The moons are on clocks too. Enceladus cannot sustain its geological activity indefinitely. The tidal heating that keeps its interior warm comes from gravitational interaction between Enceladus, Saturn, and the other moons, particularly Dione, with which it shares an orbital resonance. That resonance is not guaranteed to last. If it shifts, if the orbits evolve even slightly, the heating could decrease, the ocean could begin to freeze, the geysers could stop. The E-ring would fade without its source. Enceladus would become what it appears to be from the outside, a dead world of ice. Titan faces a different countdown. Ultraviolet radiation from the sun is slowly destroying its atmospheric methane, breaking it apart into more complex hydrocarbons that settle to the surface. This photolysis is irreversible. Without a source to replenish the methane, possibly cryovolcanic eruptions from Titan's interior, the atmospheric methane should be exhausted in a few tens of millions of years. The atmosphere will gradually lose its greenhouse capacity. The methane rain will stop. The lakes and seas will evaporate or freeze. Titan's eerie, Earth-like weather cycle will shut down, leaving a cold, inert world beneath a thinning orange sky. We met these worlds alive. They will not stay that way. The sun's red giant phase will not end things for Saturn, but it will change them. The increased luminosity will warm the outer solar system in ways we can barely imagine. Titan might briefly experience temperatures closer to Earth's current range. The ice on Enceladus could melt more aggressively. For a cosmically brief period, the outer solar system might become more hospitable than the inner system has ever been. Hold that thought for a moment. It is a strange and gorgeous consolation, but it will not last. After the red giant phase, the sun will shed its outer layers into space, forming a planetary nebula, a brief, luminous shell of glowing gas. What remains will be a white dwarf, a dense Earth-sized remnant cooling over trillions of years. Saturn will continue to orbit it, but with the sun's mass reduced to roughly half its current value, the gravitational leash will loosen. Saturn's orbit will widen, and over trillions of years, interactions with passing stars will alter it further. There are three possible ends. Saturn might be ejected from the solar system entirely, becoming a rogue world drifting through interstellar space, or it might slowly spiral inward and be consumed by the fading white dwarf, or it might simply persist, orbiting the dead star in cold, silent stability for eons beyond human comprehension. We do not know which fate awaits Saturn. The timescales involved are so vast that prediction becomes meaningless. What we do know is this: everything we see today is temporary. The rings are temporary, the hexagon is temporary, the storms are temporary, the geysers of Enceladus are temporary, the methane seas of Titan are temporary, the diamond rain falling in darkness through the interior is temporary. All of it is a snapshot, a single frame in a story that stretches from the collapse of a dust cloud 4 billion years ago to the heat death of the universe itself. And in that single frame, we exist. We built a spacecraft. We sent it on a 7-year voyage across the solar system. We threaded it through the gap between a planet and its rings. We flew it through the geysers of a moon that might harbor life. We listened to its signal for 20 years, and then we watched it fall into the atmosphere of the planet it had studied, sending data until the very last second, becoming in the end part of the world it came to understand. Saturn does not care that we did any of this. It does not know we exist. It is a ball of hydrogen and helium spinning in the dark, obeying the same laws of physics that govern every atom in the universe. It has no purpose. It has no meaning beyond what we assign to it. And yet, when you look at Saturn through a telescope, even a small one, even for the first time, something happens. The rings resolve, the banding appears, a moon or two becomes visible as tiny points of light, and you realize you are looking at something real, not an image, not a rendering, a place, a world, a system of worlds with oceans and storms and chemistry and maybe, just maybe, life. Saturn is frightening because it is magnificent and it is dying. The rings are falling. The storms are erupting and fading. The moons are ticking down on geological clocks we cannot rewind. Everything about Saturn is temporary, and everything about it is extraordinary. We are a species that built a machine, flew it 1 billion miles, and used it to discover that a tiny moon 300 miles across is shooting an ocean into space. We are a species that found a hexagon on a gas giant and spent decades trying to understand it. We are a species that measured ring rain and diamond precipitation and helium separation in the interior of a world we will never set foot on. And we are a species that, when the mission was over, when the fuel was spent, when there was nothing left to do, chose to destroy our own creation rather than risk contaminating a world that might hold life. That is what Saturn teaches us. Not just about the universe, about ourselves.